Welcome to the CoS Overview module. By the end of this module, you should be able to describe the purpose and benefits of CoS. IP routers normally forward packets independently, without controlling throughput or delay. This type of packet forwarding, known as best effort service, is as good as your network equipment and links allow. Best effort service is sufficient for many traditional IP data delivery applications, such as email or web browsing. However, newer IP applications, such as real-time video and audio or voice, require lower delay, jitter, and packet loss than the simple best effort networks can provide. Class of service or CoS features enable a Juniper Networks device to improve its processing of critical packets while maintaining best effort traffic flows, even during periods of congestion. Network throughput is determined by a combination of available bandwidth and delay. CoS dedicates a guaranteed minimum bandwidth to a particular service class by reducing forwarding queue delays. CoS settings do not affect the other two elements of the overall network delay: serial transmission delays determined by link speeds and propagation delays determined by media type. Note that CoS neither makes a network faster nor reduces congestion. Normally, packets are queued for output in their order of arrival, regardless of service class. Queuing delays increase with network congestion and often results in lost packets when queue buffers overflow. CoS packet classification assigns packets to forwarding queue on the basis of service class. CoS works by examining traffic entering at the edge of your network. The edge devices classify traffic into defined service groups, which makes possible for the special treatment of traffic across the network. For example, voice traffic can be sent across certain links, and data traffic can use other links. In addition, the data traffic streams can be serviced differently along the network path to ensure that the higher-paying customers receive better service. As the traffic leaves the network at the far edge, you can reclassify the traffic. To support CoS, you must configure each device in the network. Generally, each device examines the packets that enter it to determine their CoS settings. These settings then dictate which packets are first transmitted to the next downstream device. In addition, the devices at the edges of your network might be required to alter the CoS settings of the packets transmitting to the neighboring network. An example of CoS operating across an ISP network is shown. As each packet enters, Router A examines the packet's current CoS settings and classifies the traffic into one of the groupings defined by the ISP. This definition enables Router A to prioritize its resources for servicing the traffic streams it is receiving. In addition, Router A might alter the CoS settings of the packets to better match the ISP's traffic groups. When Router B receives the packets, it examines the CoS settings, determines the appropriate traffic group, and processes the packet according to those settings. Router B then transmits the packets to Router C, which performs the same actions. Router D also examines the packets and determines the appropriate group. Because it sits at the far end of the network, the ISP might decide once again to alter the CoS settings of the packets before Router D transmits them to the neighboring network. Note that the devices should treat traffic consistently throughout the entire network. On Juniper Networks devices, you configure CoS functions using different components. These components are configured individually or together to define CoS services. The example displays the relationship of the different CoS components with each other and illustrates the sequence in which they interact. The solid lines show the direction of the packet flow in a device. The upper row indicates an incoming packet, and the lower row an outgoing packet. The dotted lines show the inputs and outputs of the CoS components. Classifiers and policers perform these operations on incoming packets. A classifier examines an incoming packet and assigns a forwarding class and a loss priority to it. Based on the forwarding class, the packet is assigned to an outbound transmission queue. Input policers meter traffic to see if the traffic flow exceeds its service level. Policers might discard the packet or change the forwarding class and loss priority. The scheduler map and rewrite rules perform these operations on the outgoing packets. Scheduler maps are applied to interfaces and also associate the outgoing packets with a scheduler and a forwarding class. The scheduler defines how a packet is treated in the output transmission queue based on the configured transmit rate, buffer size, priority, and drop profile. The buffer size defines the period for which a packet is stored during congestion. The scheduling priority and transmit rate determine the order in which a packet is transmitted. The drop profile defines how aggressively a device drops packets that are using a particular scheduler. Output policers meter traffic and might change the forwarding class and loss priority of a packet if a traffic flow exceeds its service level. The rewrite rule writes CoS information to the packet header. Often the CoS information is stored as diff-serve code point or DSCP bits. This information is then carried to the next work device where it can be read and processed. The rewrite rule writes information to the packet according to the forwarding class and loss priority of the packet. Note that CoS support varies between platforms running Junos OS. For detailed support information, refer to the documentation on your specific platform. Forwarding classes enable you to group packets for transmission and to assign packets to output queues. The device associates traffic with a forwarding class during the classification process. During output, the system assigns traffic to a particular output queue based on a forwarding class and rewrites behavior aggregate or BA markers based on the forwarding class. Thinking of forwarding classes as output queues is tempting and sometimes helpful because a one-to-one mapping of forwarding classes and output queues usually exists. However, that definition is not necessarily true because some platforms support more forwarding classes than queues. In these cases, combining the concepts of forwarding classes and output queues can be confusing. Packet loss priorities, or PLPs, enable you to set the priority for dropping packets. You can use the PLP setting to identify packets that have experienced congestion. Typically, you mark packets exceeding some service level with a high loss priority, that is, a greater likelihood of being dropped. You set PLP by configuring a classifier or a policer. If you choose to configure random early detection or RED, you can choose different drop probabilities for traffic with different loss priorities. Welcome to the Junos OS Traffic Classification module. By the end of this module, you should be able to implement traffic classification within Junos OS. Classifiers assign packets to a forwarding class and also assign them a loss priority value. Junos OS supports two general types of classifiers: multi-field classifiers and behavior aggregate or BA classifiers. Multi-field classifiers examine multiple fields in the packet header, such as the source and destination address, and the source and destination port number within the packet. With multi-field classifiers, you set the forwarding class and loss priority of a packet using firewall filter rules. BA classifiers examine the class of service or CoS value in the packet header. The CoS value is put in the header by an upstream application or device. The value in this single field determines the CoS settings applied to the packet. There are two deployment models for CoS. In some networks, CoS is used to provide differentiated forwarding services through a single device. In other networks, the CoS deployment provides differentiated services across multiple devices within a network. With deployment limited to a single device, the system typically classifies packets as they pass through using a multi-field classifier, then uses the classification to provide the configured service level and forwards the packets without any CoS markings. However, when the deployment crosses multiple devices, the classification usually occurs differently. When you configure multiple devices in a network to use CoS to provide differentiated services, it is usually beneficial to initially perform the classification on the edge device and then transmit that classification within the network by putting BA markings in the outgoing packets. In this model, the edge device classifies traffic using a multi-field classifier as traffic enters the network. When the edge device transmits the packet into the network, it marks the packets with BA values. The rest of the devices in the network read the BA values and automatically set the correct forwarding class and loss priority without a multi-field classifier. Using BAs in network-wide CoS applications provides several advantages. First, it ensures consistent CoS treatment of the traffic throughout the network. Second, it simplifies the task of creating and maintaining accurate multi-field classifiers on each system. Without BAs, each device must have a multi-field classifier capable of classifying all traffic entering the network, and you would need to replicate any classification change on all other devices. You configure multi-field classifiers just like regular firewall filters. You place the forwarding class and loss priority in the then clause of each term. The default is to not change the forwarding class from the forwarding class assigned by the BA classifier, or if a BA classifier did not classify the packet and assign the forwarding class. Because Junos devices apply multi-field classifiers after BA classifiers, multi-field classifiers always override the forwarding class and loss priority assigned by the BA. A rewrite rule modifies the appropriate CoS bits in an outgoing packet. Modification of CoS bits enables the next downstream device to classify the packet into the appropriate service group. Rewriting or marking outbound packets is useful when the device is at the border of a network and must alter the CoS values to meet the policies of the targeted peer. A rewrite rule examines the forwarding class and loss priority of a packet and sets its bits to a corresponding value specified in the rule. Typically, a device rewrites CoS values in outgoing packets on the outbound interfaces of an edge device to meet the policies of the targeted peer. After reading the current forwarding class and loss priority information associated with the packet, the transmitting device locates the chosen CoS value from a table and writes this CoS value into the packet header. You apply rewrite rules under the Edit Class of Service Interfaces hierarchy. For example, to apply the default IP precedence markings, type Set Unit Rewrite Rules INET Precedence Default. A BA classifier operates on a packet as it enters the device. Using BA classifiers, the device can aggregate different types of traffic into a single forwarding class so that all the types of traffic will receive the same forwarding treatment. The CoS value in the packet header is the single field that determines the CoS settings applied to the packet. BA classifiers enable you to set a packet's forwarding class and packet loss priority based on the diffserv code point or DSCP value, DSCP IPv4 value, DSCP IPv6 value, IP precedence value, MPLS EXP bits, or IEEE 802.1p value. More information about these header fields can be found in the Juniper technical documentation. Once a packet is marked with the BA value, downstream devices will read those markers and automatically assign packets the correct forwarding class and loss priority. To start this process, you apply a BA classifier to the inbound interface. You apply BA classifiers to interfaces under the Edit Class of Service Interfaces hierarchy. For example, to apply the default IP precedence BA classifier, type Set Unit Classifiers INET Precedence Default. You can look at BA classifiers and rewrite rules as two sides of the same coin. A BA classifier reads the code point bits of incoming packets and classifies the packets into forwarding classes. Then the system applies the CoS configured for the forwarding class to those packets. Rewrite rules change the code point bits just before the packets leave the system, so that the downstream device can apply the appropriate level of CoS to the packets. Within Junos OS, default rewrite rules are stored in the packet or frame headers using the DSCP, IP precedence, MPLS EXP, or IEEE 802.1p standards. The example shows the default rewrite rule and classifier based on IP precedence value. In addition to classifiers, policers can also be used to set the forwarding class or loss priority of a packet. Policers enable you to limit certain kinds of traffic to a specified bandwidth and burst size. You can configure Junos devices to assign a different forwarding class or loss priority to traffic exceeding the configured limits. You can configure these policers like a regular traffic policer using the forwarding class and loss priority statements in the then clause of the policer. The forwarding class and loss priority statements from the policer override any forwarding class and loss priority statements in the firewall filter's then statement. For example, the filter assigns traffic within the specified rate limit to the expedited forwarding class. The policer assigns traffic that exceeds the specified rate limit to the best effort forwarding class. Although this is not shown in the example, you must apply the Apply CoS Markings firewall filter to the proper interface for the traffic classification to function properly. Note that some platforms running Junos OS support only a subset of the available policer actions. Check the current documentation for your product for support information. Welcome to the Junos OS Traffic Queuing module. By the end of this module, you should be able to describe the traffic queuing within Junos OS. When traffic reaches the outbound interface, the system places traffic associated with each forwarding class in its own queue. The number of queues supported on outbound interfaces is hardware dependent. Devices running Junos OS associate each forwarding class with a queue number. The default forwarding classes for most platforms running Junos OS and their associated queue numbers are displayed. By default, Junos OS sends certain network control traffic, routing protocol messages, keep alives, and so forth, to the queue associated with the network control forwarding class, typically Q3, whereas all other traffic is sent to the queue associated with the best effort forwarding class, typically Q0. You must configure a classifier to send traffic to any other queue. After the system places traffic in the correct queues, a scheduler defines how the interface should process traffic from each queue. You create forwarding classes by associating them with queues in the Edit Class of Service Forwarding Classes hierarchy. If you attempt to define forwarding classes for more queues than your hardware can support, the system displays an error message when you attempt to commit the configuration. You must associate a forwarding class name with a queue to use that queue. The default forwarding class names are associated with queues 0 to 3 on most platforms running Junos OS. You can change the default forwarding class names. If you rename the default forwarding class names, the software still sends traffic to the corresponding queues. Additionally, the default behavior aggregate or BA classifiers and rewrite rules map traffic to and from the associated queues, again typically queues 0 to 3, regardless of the forwarding class names associated with those queues. In addition to changing the default forwarding class names, you can also assign forwarding class names to non-default queues. Forwarding classes are important because all other class of service or CoS rules reference forwarding classes rather than queues. The software maintains the mapping between forwarding class names and queue numbers only in the forwarding class definitions in the Edit Class of Service Forwarding Classes hierarchy. Welcome to the Junos OS Traffic Scheduling module. By the end of this module, you should be able to configure traffic scheduling within Junos OS. You control the way the system services queues by configuring schedulers and scheduler maps. A scheduler contains parameters that describe how to service a queue. A scheduler is associated with a particular queue and forwarding class through a scheduler map. You define the order in which packets should transmit by defining a priority and a transmission rate for a forwarding class. Devices running Junos OS typically transmit packets from forwarding classes or queues with a higher priority before those with a lower priority. The default priority values might vary between Junos devices. You can configure a transmission rate for each forwarding class. The transmission rate controls how much bandwidth the traffic associated with a given forwarding class can consume. By default, the software assigns 95% of the bandwidth to the queue associated with the best effort forwarding class, typically Q0, and 5% of the bandwidth to the queue associated with the network control forwarding class, typically Q3. The software assigns all other queues a zero transmission rate. By default, all queues can exceed their assigned transmission rate if other queues are not fully utilizing their assigned rates, unless you configure the transmission rate with the exact option. The configured buffer size determines the size of each queue. As previously mentioned, by default, the software assigns buffer space only to the queues associated with the best effort and network control forwarding classes. By default, all other queues have 0% of the available buffer space. Therefore, if you use queues other than those associated with the best effort and network control forwarding classes, you should assign buffers to those queues. As the buffer fills, the likelihood that the random early detection or RED algorithm will drop packets increases. You can specify an exact RED drop profile for each queue. However, the default configuration is to not drop packets until the queue is full, and only then drop packets. Note that not all platforms running Junos OS support RED. Check your product-specified documentation for CoS support information. Junos OS supports multiple levels of transmission priority, which in order of increasing priority are low, medium, high, high, and strict high. Using this priority structure enables Junos OS to service higher priority queues before lower priority queues. Priority scheduling determines the order in which an output interface transmits traffic from the queues, thus ensuring that queues containing important traffic receive better access to the outgoing interface. This procedure involves the software examining the priority of the queue. In addition, the software determines if the individual queue is within its defined bandwidth profile. The higher priority queues transmit packets ahead of the lower priority queues, as long as the higher priority forwarding classes retain enough bandwidth credit. Note that when you configure a higher priority queue with a significant fraction of the transmission bandwidth, the queue might lock out or starve the lower priority traffic. Strict priority queuing works differently on different platforms. For platform-specific details and behavior, refer to the documentation for your specific product. A drop profile is a feature of the RED process that enables packets to be dropped before queues are full. Drop profiles are composed of two main values, the queue fullness and the drop probability. The queue fullness value represents the percentage of memory used for storing packets in relation to the total amount that has been allocated for that queue. The drop probability is a percentage value that correlates to the likelihood that an individual packet is dropped from the network. Randomly dropped packets are counted as RED dropped, while packets dropped for other reasons are counted as tail dropped. You specify drop probabilities in the drop profile section of the class of service configuration hierarchy and reference them in each scheduler configuration. For each scheduler, you can configure multiple separate drop profiles, one for each combination of loss priority, low, medium high, or high, and IP Transport Protocol, TCP, or non-TCP, or any. By default, if you configure no drop profiles, RED is still in effect and functions as the primary mechanism for managing congestion. In the default RED drop profile, when the fill level is at 0%, the drop probability is 0%. When the fill level is at 100%, the drop probability is 100%. You can configure RED drop profiles at the Edit Class of Service Drop Profiles hierarchy level of the configuration, with a maximum of 32 different drop profiles. You can configure schedulers under the Edit Class of Service Schedulers hierarchy. The name of the scheduler has no special significance. Junos OS associates schedulers with individual forwarding classes and queues using scheduler maps. In the example, Junos OS uses the scheduler for traffic in the best effort forwarding class. Therefore, it is named as SCHED-BE to remind you of its purpose. However, it could have been named anything and still associated with the best effort forwarding class in the scheduler map. In this example, the buffer size is configured to be the same as the transmit rate. This practice should perform acceptably under many circumstances. However, cases exist where different buffer sizes are appropriate. You can find more details in the Junos Class of Service Configuration Guide. Also, a custom drop profile BE drop profile is configured in this example. Scheduler maps associate schedulers with particular forwarding classes and their respective queues. Junos OS references queues by the name of the forwarding class associated with them. You can configure scheduler maps under the Edit Class of Service Scheduler Maps hierarchy. In this example, 4 schedulers are associated with the 4 default queues. The last step in configuring a device running Junos OS to service its queues is to associate the scheduler map with an outbound interface. When packets arrive at the output interface, the system places the packets in the appropriate queue for the forwarding class of the traffic. The system determines the order in which to transmit packets from the queues by referring to the parameters configured in the scheduler associated with the given queue. The scheduler map informs the system which scheduler should be associated with each queue on a particular interface. You can use different scheduler maps on different interfaces to specify different scheduling parameters for queues on a per-interface basis. The scheduler applies to all traffic across a physical interface unless you configure per-unit scheduler for the interface under the Edit Interfaces hierarchy. In that case, the system schedules packets on a per-unit basis, and you can also define different scheduler maps for each unit. Note that support for per-unit schedulers varies between platforms running Junos OS. Take a look at this diagram. It will help you understand how these concepts fit into the big picture. Note that the CoS support varies between platforms running Junos OS. For detailed support information, refer to the documentation on your specific platform. Welcome to the CoS Use Case module. By the end of this module, you should be able to implement CoS for a given use case. The example shows a simple topology with an across-the-network class of service, or CoS application. Note that the CoS support varies between platforms running Junos OS. In this example, R1 and R2 are SRX series devices. The traffic classification and scheduling rules, as well as the forwarding classes and queue mappings, are shown. For simplicity, use the same scheduling rules for all traffic on all interfaces. Note that once traffic is associated with queues other than Q0 and Q3, you must configure a scheduler for those queues on all interfaces. Failure to do so might lead to serious performance problems for traffic that exits an interface through a queue that has no defined scheduler. The example shows the configuration necessary for implementing the defined classification rules on R1. The first term from professors matches traffic with source address of 192.168.25.64/26, and if it matches, it then applies the forwarding class name professors and accepts it. The second term students matches traffic with source address of 192.168.25.128/25. And if it matches, it then applies the forwarding class name, students, the policer named student policer, and accepts it. The third term, default, as there is no from clause, matches all and permits all traffic. You can view the detailed configuration and topology from the resources section of this module. The example shows the configuration necessary for implementing the specified classification rules on R2. The first term, to professors, matches traffic with source address of 192.168.25.64/26, and if it matches, it then applies the forwarding class name professors and accepts it. The second term, to students, matches traffic with source address of 192.168.25.128/25, and if it matches, it then applies the forwarding class name students and accepts it. The third term, default, as there is no from clause, matches all and permits all traffic. You can view the detailed configuration and topology from the resources section of this module. The example shows the forwarding class, scheduler, and scheduler map configuration for both routers. The four schedulers used in this example are Sched Network Control. It has transmit rate, buffer size of 5, and priority set to high. Sched Professors. It has transmit rate, buffer size of 45, and priority set to medium-high. Sched Students. It has transmit rate, buffer size of 40, and priority set to medium-low. Sched Best Effort. It has transmit rate, buffer size of 10, and priority set to low. Devices running Junos OS typically transmit packets from forwarding classes or queues with a higher priority before those with a lower priority. By default, all queues can exceed their assigned transmission rate if other queues are not fully utilizing their assigned rates, unless you configure the transmission rate with the exact option. Note that the forwarding class and scheduler configuration is identical on R1 and R2. You can view the detailed configuration and diagrammatic representation of scheduler map from the Resources section of this module. The example shows the Behavior Aggregate or BA classifier and rewrite application, as well as the scheduler map application for both routers. The scheduler map professor-student scheduler is applied on both routers' incoming and outgoing interfaces. Classifier and rewrite rules are applied on the outgoing interface of router R1, GE/0/0/3, and incoming interface of router R2, GE0/0/3. You can quickly see most of the CoS configuration for an interface using the Show Class of Service Interface Name command. This command displays the active configuration, including default values. You can use other Show Class of Service commands to display details about various components of the CoS configuration. For example, to see how the IPP-REC default classifier maps the type of service field in the IP header to a forwarding class, execute the Show Class of Service classifier name IPP-REC default command. One of the best ways to ensure that the CoS configuration is performing as expected is to ensure that traffic is placed into the expected queues on output. On most interfaces, you can determine summary statistics for each queue using the Show Interfaces Detail and Show Interfaces Extensive commands. For some encapsulation types, these statistics are not available with this command. You can also see how traffic is being queued using the Show Interfaces Queue command. This command shows much more detailed statistics for each queue and is available for all interfaces. Based on this example, you can determine that traffic is being queued correctly.